So I got a problem with a nonlinear device.
Is it a varactor-tuned device like an oscillator or a filter?
No.
Is it a pin attenuator, a series or shunt one?
Nope.
Some kind of chemical sensors, gas, liquid, enzyme?
I guess again, it's a real problem.
Okay, maybe a distance sensor, optical?
No.
Magnetic?
Nope.
Capacitive?
Nope. Anyway, why are you asking? What do all these different kinds of things have in common?
They're all devices that don't naturally have a linear input-to-output transfer characteristic, but if you connect them through an Impelmax linearizer, ta-da, they can be linear.
What's a linearizer? Is it like a rack-mounted piece of equipment?
No, it's smaller. It can be a hybrid circuit no bigger than your pinky fingernail, and it can take one transfer function and convert it to a different function that you like better. Almost always, that means taking an exponential tuning curve.
Like a pin attenuator current versus attenuation graph?
Right. Taking one of those curve transfer functions we just saw and making it into a straight line.
Oh, like 10 dB per volt, straight line? Neat. But that won't help me.
Why not? What kind of nonlinear transfer function problem do you have?
It looks like a camel on a hill, walking backwards.
Oh.
Yeah, it's a complicated system and there's a whole chain of parts. It has to be stable over a wide temperature range. But it turns out that some of the parts go this way over temperature, and then other pieces in the chain are good until a certain temperature, and then they go shifting, et cetera, et cetera. Okay. There's a bias control on one of the items in the chain, and if I could only adjust the bias knob according to the temperature, I could flatten out and fix the temperature dependence on the whole system. I can easily generate a voltage proportional to the temperature with a single DigiKey IC. So that seemed like a good solution. But when I graphed the bias I needed over the temperature range of the part, that's when I got the camel on a hill, walking backwards. So I don't think your linearizer idea is going to work for me.
No, actually it will.
How?
Let's get a quick understanding of how a linearizer works for a simple case first. Let's start with the shunt pin attenuator curve. If you plot the desired attenuation on the horizontal x-axis, and for each attenuation level you plot the amount of diode current you need for that attenuation, you get a concave up transfer function like this.
That's pretty nonlinear.
We've dealt with bigger slope ratios than this even, but this is sort of a typical example. An Impelmax linearizer has a block diagram something like this. The input buffer provides a 15K input impedance, and it feeds a signal to the set of breakpoint current sources. The external resistors are user-defined.
Okay, so I connect resistors to the pins, and that sets it for my particular curve?
Right. Well, we can put them inside once you know what resistor values you need. They function in pairs to set the turn-on point and the gain of each breakpoint current source. The breakpoint current sources sum together into the output current mirror, which results in the linearizer output current.
Okay, so the output current of the linearizer goes right to the shunt pin diodes in this case.
Yeah, simple as that.
But what if you need voltage output, like you're driving a varactor tuning diode?
Then you can dump the output current into a load resistor, and there's your voltage.
How's it work?
For this example, let's say you need a 30 dB range on your attenuator, and the customer wants to drive it with a 0 to 5 volt signal. So figure the linearizer is being driven by a linear ramp from 0 to 5 volts. With no breakpoint resistors connected to the linearizer, the output is 0 milliamps for any voltage on the input. Next, for this example, we'll start by connecting a single resistor instead of a pair, like we're going to do for the other breakpoints, to ground. This makes the first breakpoint turn on at 0 volts. The gain of the breakpoint is set by the value of the resistor.
You put a 1K. What if you put a 500 ohm instead?
If we cut the value in half, the gain of the breakpoint doubles. The output of the linearizer now goes up twice as fast given the same tuning input ramp. If we double the ohms of the breakpoint, the gain drops to half.
Okay.
If we now add a second resistor, which connects to a reference voltage, the turn-on point of the breakpoint shifts up from 0 to equal the open circuit voltage of the two resistor divider. Here we have a 1K resistor to ground and a 1K resistor to plus 10 volt. If we keep the 500 ohm Thevenin impedance of the resistor pair, but use different values so that the center node voltage is higher or lower, we find that the turn-on voltage of the breakpoint follows it identically.
Okay, I get it. For each of the breakpoint pins, you can control what voltage they come on at and at what rate or steepness. And all the currents from the breakpoint pins are summed up and mirrored in the output?
Exactly. If we set up one breakpoint with a resistor to ground, say 1K, and a second breakpoint is set up with the dual 1K resistor pair like we just demonstrated, we find that the output voltage of the Impelmax linearizer is the additive total of the two breakpoints. We have just synthesized a very rudimentary linearizer curve.
Got it.
But you've got a camel problem.
Big time.
The shunt pin example was kind of a C-shaped problem, concave up, more or less exponential. If it had been a series diode attenuator, it would have been a C-shaped, but concave down. Do you know how we linearize that?
I don't see how you can make that kind of curve with the linearizer method you just showed me.
Quite right. So we use reverse direction breakpoints. You can think of them as already on at 0 volts, and at some point, defined by their rate, they shut off. The same rules apply, so just like in the first case, we can independently control the rate and position of each breakpoint, And that lets us synthesize concave down curves like this one for a series pin attenuator.
What about if you need a curve like this?
What's that for?
I don't know. Let's just say you had a curve like this from an ultrasonic laser transmorgifier beam sensor or something. I don't know. Can you linearize that?
Okay, yeah, no problem. Actually, Impellimax linearizers that have cut breakpoints are what you'd need here. They work a lot like the first example.
The shunt pin attenuator example?
Yep. The difference being that instead of mirroring the breakpoint current to the output additively, a cut breakpoint pin has its current mirrored subtractively. So as the cut breakpoint comes on,
From left to right, just like in the first example.
yeah, it reduces the output current by that amount.
Oh, I'm starting to have hope for my Camel.
You should.
Can a single Impellimax linearizer combine cut breakpoints and regular breakpoints?
Yeah, and reverse breakpoints as well.
Oh, so for my camel-shaped graph, I could just go cut from 0 degrees at whatever rate I need.
And set up a regular boost breakpoint at about 10 degrees and a cut here.
And a boost and a cut and one last boost. Hey, this could really work.
Yes, it does work. And all the hardware to do this could easily fit in a postage stamp-sized area. And it can be made hermetic or high-rel for military space applications, no problem.
After the Camel, I'll just get other nightmare problems.
And sometimes you can just use the same Linearizer hybrid but set up differently. It cuts your learning curve not having to design the wheel every time.
It helped that I could talk it over with you. I'd have a harder time doing it alone.
Well, you can keep doing that. Impellimax is always here for answers and assistance. You can email or call with your problems or data, and we'll work with you all the way down to calculating the resistors and even laying out a demo PC board if that's what it takes. There's also our free software that you can use to automate the resistor calculations graphically. We've been producing Linearizer hybrids for over 15 years, so there's a lot of history and experience available to you when you call.
What about when breakpoints turn on or off? It makes them sound like they're digital with that on and off talk.
They're not digital. They're analog and with natural tailing and rounding in a transition, so they're smooth as glass.
No stair stepping?
None whatsoever. And linearizers can be pretty fast, so nice smooth modulation is easy if that's what you need. You just can't get good modulation performance from a prom-based linearizer. Control loops hate proms, and they love our linearizers.
And I can make it have a voltage output or use it directly as a current output?
Yes, and you can have multiple outputs all doing the same thing pretty easily. And if you think about it, you can put an Impellimax linearizer before the device,
Like when you're driving an attenuator or a VCO?
right, to make the device tune linearly. Or you can put it after the device.
So if you had a chemical sensor or an optical sensor that puts out a nonlinear signal,
Then the Impellimax linearizer hybrid can take the nonlinear output and provide a linearized output.
sweet.
Or, as in your case, we're putting a linearizer between two devices
A temp sensor in my bias sensitive part.
for best system performance over temperature.
Oh, I think you just saved my Camel.
You're welcome.